we present a method for obtaining focus and context views in the presence of deformation. Our approach is a generalized method that applies to continuous data as well as to discrete. An important aspect of illustrative deformation is the preservation of focus of attention. Here, we deform a tornado dataset to get a better view of internal flow. To match the shape of the focus, the user draws a curve, which is used by our framework to obtain a clearer view. To elucidate the relation between focus and context, it is necessary to mark up contextual regions via optical transformations. Here, the user deforms a thermal plume dataset. The context is de-emphasized to provide a better view of the internal structures. Here, the user applies deformation to the fuel simulation dataset to get a better view of the interior shape. An optical markup is used to highlight the areas undergoing deformation. Our approach extends to discrete data as well. Here, the user deforms a set of stream tubes obtained from the blunt fin flow dataset. Deformation enables the user to get a clear view of the internal flow. Note that the integrity of the streamlines in the focus is preserved. With no geometric preservation of the focus, the deformation cuts through the lines, making it difficult to understand. As a comparison, we show the effect of using only an optical transformation. Here, the user deforms the context rigidly. It can be seen that elastic deformations provide a clear view of the focus and context. One advantage of our approach, in comparison to explicit deformation, is the ability to depict soft shadows at no extra cost, necessary for better depth and motion cues. Another application of deforming implicit lines is the deformation of fiber tracts in diffusion tensor imaging. Geometric integrity of the lines is not required, as virtual cutting operations are reminiscent of physical cutting of the brain specimens. Here, the user interacts with a scatter plot of data from the early universe simulation. Spatial dimensions plot density, gas, and total energy of star particles. Color coding denotes temperature. The user is able to focus in a region by deforming the dataset. Feedback is given as a deformation icon shown in the lower left corner, and vector field arrows, depicted in red. Similarity transformations can be applied to the focus to obtain a zoomed-in view of the region of interest. Our approach also extends nicely to the cases of 25,000 points and 100,000 points. Multi-space deformation enables us to define different types of geometries for the rendering space. In this example, the user visualizes a video as a static 3D volume, where the focus is defined as a tracking feature, obtained automatically from optical flow. Mapping the 3D volume to a semi-torus allows us to make a better use of screen area. Note how deformation is automatically mapped to the new rendering space.